Welcome to our webinar on resilient timing for critical infrastructure. This webinar is presented as an introduction to topics that will be explored much more in depth at the workshop on synchronization and timing systems, WSTS. This year, WSTS will be in person in Denver on May 9 through 12. There'll be more details about WSTS at the end of the webinar. I am your moderator. My name is Mark Weiss. I'm the chair of WSTS. Here's an outline of our webinar. We'll start with a motivation for resilience. We'll proceed into our presentations. There will be 3 specific types of resilience presented, plus a 4th talk, which will be an example of resilience and assurance. Each of these will be as applied to one of 4 different verticals or industries. Finally, we'll end with a panel discussion, including questions from the audience. Please submit questions in the chat as we proceed through the webinar. Some of these may be answered as we go. There'll be short power presentations, as I said. The first will be redundancy and monitoring in media and broadcast, presented by Doug Arnold, Principal Technologist of Mindberg. The second is solutions for backup resiliency in finance and data centers, by David Chandler, Product Line Manager of Microchip. Third, diversity of sources beyond GNSS in telecom. Anand Ram, Vice President, Business Development of Calnex. And finally, an example of resilience and assurance in power systems, presented by Dina DeFalcius, Senior Director of Business Development, Oscilloquartz. And then we'll move on to our panel. So, why do we need resilience? Well, critical infrastructure is vulnerable to a variety of timing problems. Loss or degradation of timing can be due to intentional or unintentional effects. Intentional effects can include jamming or spoofing of global navigation satellite systems, GNSS. There can be cyber attacks on data systems, much as in computers, there can be cyber attacks. PNT systems have computers in them, and those can be attacked in similar ways. There can be timing attacks on timing networks. Then there are unintentional effects. The sun can cause significant disruption of GNSS signals and any kind of radiated signals. There can be radiated radio frequency noise that can cause unintentional jamming. And finally, there can be system failures of any kind that can cause significant disruption. Here's a quick summary of our talks. There are the 4 industries on the left, the 4 types of resiliency across the top, and the 4 speakers on the diagonal in the order in which they'll be presented. I will now pass the baton over to Doug Arnold, who will give our first presentation.
Hello, this is Doug Arnold, and I'm going to talk to you about techniques for resilient and robust timing in PTP networks for broadcast media applications. Timing is critical in broadcast and media systems. Media is captured with multiple cameras and microphones. The capture files are stored on servers with timestamps embedded in them, and for any kind of editing or other processing, the timestamps have to be lined up. Precise timing also helps, removes jitter and artifacts, helps with color accuracy, maintaining frequency for broadcast signals. And with all this, the error budget allocated for network time distribution is typically 1 microsecond. Some techniques for resilient and robust timing include the following: stable oscillators for holdover, multiple time reference sources. These will be covered by my co-presenters. Redundancy in the networks, in the GNSS receivers and time servers, and monitoring to identify any early warning signs of problem. This diagram shows 2 of the forms of redundancy that we want to have in a broadcast media network in order to guarantee high availability. First of all, there are two Ethernet spines, here shown as the blue one and the red one. The media devices are all two-port devices, and all the messages are duplicated on each network. That way, if there's a failure in one of the spines, messages can still be transmitted and received at all the media devices on the other network. In this case, they're also indicated as being PTP capable, so they're acting as either boundary clocks or transparent clocks. Now, another source of redundancy that can be added is if the time server receives its time through a GNSS receiver, that is Global Navigation Satellite System receiver, it can be a receiver that's capable of seeing multiple constellations. In this case, I showed GPS, Galileo, and Baidu. That way, if there's a system error in one of the constellations, you can still get good time from the other ones. Here we see the same diagram, except for now the time server has redundant GNSS receivers, has two of them, and each one has its own antenna. It's important that they each have their own antenna, since the antenna, after all, is probably the most vulnerable part of the system. Typically, the antennas are located on the roof and therefore are exposed to the elements, making them the most vulnerable. Even better if you can separate the antennas by as great a distance as possible. That way, if there's jamming affecting one antenna, the other one might be operating normally. One way to increase the maximum cable length to enable this is to downconvert the signal or convert it to an optical fiber signal. Of course, for maximum redundancy, you can have two completely independent time servers, one for each of the Ethernet spines. In addition to redundancy to guarantee high availability, I recommend monitoring all the PTP nodes in the network. Typically, the boundary clocks, transparent clocks, and media devices will have a rich set of information about their PTP status in their management interface. This information can be gathered and sent to the time server or to a separate monitoring node. Broadcast engineers and technicians are way too busy to dig through log files just to see if their timing is still working as expected. That's why it's important that the monitoring system have a simple visualization screen that allows them to see at a glance if everything is still operating properly. In this example, there's a kind of a bullseye target pattern with a threshold set at 1 microsecond, and we can see that one of the nodes has exceeded that. The most accurate way to measure the time performance in the network is to have a time monitor node. This would be a node that has its own source of time, such as GPS, and receives PTP and can compare those two times. It should be placed at the worst case position in the network in terms of number of network hops. That way, if the time monitor time and the PTP time agree at the time monitor, then we would expect probably the media devices are also in agreement with their requirements. Some key points in summary. Precise timing is critical in broadcast and media networks. One way to increase the reliability of that time distribution is through redundancy. We can have redundant networks. We can have GNSS receivers that use multiple constellations in case there's a system failure in one of the constellations. We can have multiple GNSS receivers, preferably with separate antennas and ideally with a maximum physical separation between those antennas. We can also have completely redundant time servers. I also recommend monitoring. You want to identify any timing issue as soon as it's happening. Time servers or other monitoring nodes can collect status of PTP nodes through their management interfaces. The most accurate indication of error of time in the network is through a monitor node that has its own source of time, such as its own GPS receiver. You place it at the worst case point in the network and check the timing there. Next up, my colleague David Chandler will talk about timing in finance and data center networks, specifically focusing on the importance of good holdover oscillators when the source of time is lost.
Thanks, Doug. Hi, I'm Dave Chandler, Product Line Manager at Microchip Technologies, and I'll be focusing on finance and data center timing applications with an emphasis on solutions for backup resiliency. Let's look at two applications. The first, in the data center market, we'll look at high-speed trading. This is an example of a regulatory-driven timing requirement. It must be below 1 microsecond accuracy. This has been flowed down both in the US and in Europe, and there's a premium on security in this application because they're concerned that people will manipulate time for their own financial gain. We switch gears and look at the data center market and look at a distributed database application. This is an example of an application-driven requirement. There's no overarching standard for data center timing overall. It really comes down to data centers are providing replications at the edge to reduce latency, but that creates linearization issues that they solve by providing tight timing. And that tight timing then allows them to increase the number of transactions per second. It allows them to have improved logs, and it allows them to recover faster in the case of a failure. Let's look at the timing requirements in the data center application in a little more detail. This has really been driven by the exponential growth in transactions per second that are occurring in data centers today. If you have thousands of transactions per second that you have to be able to support, you may choose to do that using NTP, which can achieve sub-millisecond timing, or you may have millions of transactions per second in the case of an exabyte or a petabyte database, in which case you're going to look at something like precision time protocol, or PTP, that can achieve sub-microsecond timing. And the challenge here isn't really just synchronizing two servers within one data center, but it's synchronizing across multiple data centers. So those data centers may be separated by hundreds of miles, and they may be separated by fiber. They may be, separated and being communicated through the cloud. In all these cases, you need to have some form of external synchronization to ensure that all your servers are synchronized. So why would you want to have replications of a distributed database all across the world? Well, let's look at the example of a user in Los Angeles and a database in New York. The fastest possible transfer of information from Los Angeles to New York is 13.1 milliseconds. That is limited by the speed of light. That's it. You can't go any faster. A single read request requires a two-way transmission. That's limiting you to 26.1 milliseconds. Now let's look at the real world. Let's take fiber, which is one of the fastest means of being able to communicate. You're going to have to deal with the refractive index of the fiber. You're going to have to deal with the real world path of the fiber. Now you're talking 3 to 4 times what you originally saw. So you're at about 100 milliseconds. 100 milliseconds means you've only got 10 read requests that you can do in a second. This obviously is not a good solution in a world where we have databases today that require about 500,000 transactions per second. The way data center providers get around this problem is to add a replication of the database right next to the user. This limits the latency, but now it adds the complication of needing to have synchronization between both databases. The way they achieve synchronization is typically by providing an external time source, which is typically UTC, and then they ensure that there's some type of means to do accurate time stamping for each transaction in those data centers. Ultimately, the clock uncertainty and the time stamping uncertainty will determine the TPS that the data center can provide. There are 3 elements to precise time in a data center. The first is you need to ensure you have some means of getting traceable time to UTC, and it must be secure. This is typically done using a GNSS constellation, Galileo, GLONASS, or GPS, or maybe all 3. You need to make sure that you have addressed spoofing and jamming in some fashion when you use a GNSS source. The next is you need to have a backup in case GNSS goes out. This is typically done with a quartz crystal oscillator or an atomic clock. And finally, you need to be able to distribute that time once it's in your data center to all your servers. It's typically done using NTP or PTP. How do we get time from the GNSS constellations down to the individual servers in the data center? One route would use a public time server that would then transmit via NTP over the internet to the servers in your data center. This has some inherent problems with security, capacity, speed, and resiliency. An alternate solution is you could use a time server or a time appliance that you put within the firewall of your data center and then distribute NTP or PTP to your servers from there. This improves your security, it improves your capacity, it improves your resiliency by allowing you to have an alternate time source that can communicate to that time server, whether it's an oscillator, an atomic clock, or some other type of device. So let's talk about those local oscillators that are your resiliency solution or your backup time when GNSS goes out. Your requirement may be for 30 minutes of holdover. Your requirement may be for a month of holdover. There's no standard industry requirement at this point. 24 hours is a typical thing that telco guys had, so I use that as an example here. Start on the far left. We have MEM solutions that cover you from hundreds of milliseconds down to hundreds of microseconds today. We then have quartz solutions that from crystal oscillators, temperature compensated crystal oscillators, and oven controlled crystal oscillators can take you from the millisecond region down to right around 1 microsecond. And then you pick up with the atomic clocks. You start with your chip scale atomic clock, you go into rubidiums that are holding right about that sub-microsecond region, down to your cesiums, which cover you in the nanosecond region, and you can even get into hydrogen masers that now start covering you in picosecond regions every 24 hours. There are different timing solutions for different applications. A hyperscale data center might require 100 nanosecond holdover for a period of 1 week. You may choose to use a cesium for this requirement. A co-location data center provider might be providing time as a service to his clients, and maybe he needs 1 microsecond over 48 hours, and he's choosing a rubidium for this. Finally, the client, if he chooses not to get the time from the provider, but provides his own time, may be able to get away with 1 microsecond over 30 minutes, in which case he may be able to use a quartz crystal oscillator or a MEMS oscillator. And with that, I'd like to hand it over to Anand Ram from Calnex, who's going to talk about alternate time sources other than GNSS. Thank you.
Hello, welcome to the presentation on resilient timing for critical infrastructure with reference to the telecoms industry. Specifically today, we're going to be looking at the mobile network infrastructure, its requirements for timing, and how resiliency is generally guaranteed for timing in these networks. We're also going to look at potential issues with the common methodologies used today and make some recommendations. My name is Anand Ram, and I'm from Calnex Solutions. Today's webinar is following the theme of resilient timing, and we're going to be talking about having diversity of sources in the telecoms network, specifically referring to the mobile network. How there is usually a primary and a secondary or backup reference for timing to facilitate the mobile network operation. But let's start by looking at the fundamental requirements of timing and synchronization in a mobile network. The standards for mobile networks are governed by the 3GPP, the standard quoted in this slide, which fundamentally say that the phase synchronization accuracy measured at the base station antenna connector needs to be within 3 microseconds for adjacent cells. Why? Because in time domain systems, the different time slots can be used in the same frequency for uplink and downlink transmission. If the phase synchronization isn't to these specifications, then there will be interference and ultimately degradation in performance. So synchronization is required to guarantee that there's no interference or interference is minimized. And this is interference between the base station and the mobile equipment. interference between uplink and downlink transmissions, interference between base stations, interference between mobile equipment. So the specification states that it should be 3 microsecond synchronization between adjacent cells. And this is normally implemented in telecoms networks and mobile networks as a time requirement relative to a central clock. So if the requirement is 3 microseconds between two sites, this is then implemented as a 1.5 microseconds requirement to a common or central reference. And this is how the ITU-T standards body implements the requirements of the mobile networks in a telecoms network. So the time alignment between a central clock and each base station needs to be 1.5 microseconds. So how is that delivered and deployed in today's mobile networks? Well, a common methodology in the past has been to potentially synchronize base stations, particularly in North America, directly with GNSS. But with the growth in the volume of base stations to thousands to tens of thousands, this isn't always a practical method of delivering synchronization, particularly when a lot of these cell sites happen to be indoors where there's very poor GNSS coverage. So a common deployment model has been to use a cell site router. Now this is a router or device that aggregates traffic for all of these different networks, which usually is found at the cell site, and synchronize that via GNSS, and then use PTP, or the precision timing protocol, to deliver timing and synchronization to the base station equipment. So this 1.5 microsecond requirement that you saw before is really the requirement between the time source of GNSS and the antenna on the base stations. And that generally works pretty well if your GNSS is reliable. This is generally either a single hop or a low number of hops of network, and therefore you can deliver this performance to the base stations. That is the primary synchronization for the base stations. The backup or secondary synchronization tends to come from a grandmaster deployed in the core of the network. Generally, this is transported through what we call an unaware or timing unaware network, and that provides the backup. The timing requirements for this backup are the same. They need to be 1.5 microseconds from the common clock to the antenna. And generally in the networks, this is deployed as 1.1 microseconds to the endpoint of the network, with some budget left in for the radio or base station equipment. So this is, again, a pretty common deployment model for synchronization in mobile networks. Most of the time, it relies on that primary reference, but there is also a backup reference or timing, which generally comes via the network. So this is how the idea and the engineering is done in the network to deploy that second source of timing. However, today's webinar is going to focus on a topic of why some more thought needs to go into the deployment and the operation of these networks. So one of the points we want to try and make is that while there is a backup or resilient source in this network, the primary sync is usually pretty reliable, and there is some holdover capability in that site. So again, generally, most of the time, the network will work. But with a few things that an operator might need to worry about. First, GPS or GNSS vulnerabilities are growing. GNSS spoofing, jamming incidents are increasing. GNSS issues or problems are also increasing on the growth. And so all of these things could cause an issue with the availability of the primary reference timing for the base station. In addition to that, what we showed is the last mile from that cell site router to the base station. That network is also growing. If you want to grow from 5 base stations to 5,000 base stations, you need a different architecture. And generally, you put a network in there. And when you put a network in there, that changes things and evolves things as well. So there is a lot of input here that says the primary reference may not be as reliable in the long term, and certainly needs, the need for a second source needs to be investigated. And this second source is, of course, a secondary or the backup synchronization. Very often we have seen this isn't tested, it's unqualified, it's deployed, but because it's not used, it's not truly validated or tested. The question to be asked then is it really or truly a backup? If PTP is being deployed via a network that is not PTP aware, we have seen performance issues in many networks around the world when it isn't engineered correctly. like we said, this is very often delivered via a PTP unsuitable network. And so our recommendation in CalNext is really there is a requirement to conduct an audit or regular audits of this backup synchronization. Fundamentally, we're trying to guarantee redundancy, holdover management, and monitoring, which is the theme of this webinar, to create that resilient timing. And we're saying that in a lot of mobile network deployments today, there are question marks on whether redundancy and monitoring actually exist, because the reliance is on the primary reference source. The secondary or backup synchronization is not fully qualified and really needs to be, as when the network has to fall over to its backup, you as a network operator would want to be sure that there is no compromise in service quality to the end customer. Thank you for listening to that presentation. I will now hand over to Nino De Paltis from Mozilla Quartz, who will talk about timing in the power industry. Thank you.
Hi, my name is Nino De Paltis. I'm the Senior Director, Sync Business Development America at Mozilla Quartz. Today, I'm going to be talking about an example of resilience and assurance in secure smart. Cyber threats are everywhere, higher in frequency, growing sophistication and tactics. For instance, GNSS satellite can be shot with laser ranging technology. GNSS antenna on the ground can be jammed and spoofed. Network timing can be disrupted by a hacker at scale. Therefore, smart grid needs to be protected as a critical infrastructure with a defense in-depth timing architecture. By the way, this is also specified in the Department of Homeland Security Resilient PNT Conformance Framework. The smart grid is also going through some transformation from a passive system legacy to an active ecosystem. The passive system used to be very traditional, very simple, with a centralized management or a centralized distribution, one flow direction, AC and the end user. The active is more distributed, more complex, with renewable energy, also called distributed energy resources or DERs, bidirectional, and provides AC/DC at the end users, DC for the autonomous industry, including electrical car and all the recharge capability that the smart grid needs to provide. As a result of that, the active ecosystem basically requires tighter data timestamping accuracy. So we're moving from NTP, legacy millisecond accuracy, to PTP sub-microsecond accuracy that is needed for the new active grid. Here are some applications here for the synchrophaser here, better than 1 microsecond, fault location even 100 nanosecond, PMU better than 1 microsecond, the substation for the Goose 618050 as low as 100 microsecond, and for the sample value we even have a 1 microsecond. What are the PNT cyber threat GNSS vulnerability? Two categories, external, internal. On the external, we have environmental with solar effect, very common. Volcano eruption, very rare. Jamming, common. Spoofing, rare to frequent. Some hackers are combining jamming and spoofing with a pseudo frequency to make it more difficult to detect. Adjacent band transceiver under review. A ground error, ground segment error, very rare. On the internal side, we have NTP that is very common. You can Google NTP amplification. PTP is very rare, but that doesn't mean it should not be protected. And finally, a GNSS receiver is an active component connected to the network that can be hacked and therefore has to be protected. Here I'm showing a trusted timing architecture in core station and substation. Here my assumption is that we have a major disruption of the GPS signal on two sides, but it could be multiple sides. Here we have site A, site B with a grandmaster on each side. Grandmaster A here loses the GPS because it's been hacked or disrupted. Therefore, it falls back to a cesium backup clock, an independent clock. We can add some other sources of opportunity to the cesium. All those alternative sources to GPS basically provides a trusted PTP backup to the network. We call it trusted because it's verified by an independent GPS source. The network here, which is either a legacy SONET or MPLS telecom network, uses a layer 2 telecom profile, which means full on-pass support. And what that means also is all the switches here, those 3 switches, are configured with PTP-aware boundary clock. On the substation with the Grandmaster B, since the GPS is down, it takes the trusted PTP backup from the network and then distributes the timing, legacy timing, to the substation as well as PTP profile. On top of that, each Grandmaster is configured with an integrated monitor that basically provides the analytics on multiple sources in order to compare the sources, verify them, and select the best one, the best trusted source, either for the upstream network or for the downstream network. Here in this case, we have Grandmaster A and Grandmaster B. Finally, we have the management system that has all the intelligence of the network and can make actionable decision while alerting the users in order to maintain a self-survivable timing network. And I have a slide that basically highlights how the management system should work. Here, the management system here, that is basically what we call a neural intelligent management system with self-survivable capability as well as end-to-end control. Here, the management system has the view of the geographic location of all the sites. Here, the 2 sites that went down due to GPS cyber attack, the core and the substation. Here we have the timing chain of the core and the substation with the different backup rearrangement from ePRTC to trusted PTP. Here we have the 2 Grandmaster at the core and the edge that basically takes the backup from ePRTC and provides PTP backup to the network. On the edge side, it actually takes the PTP backup since the GPS went down. Here, the timing topology, we can see ePRTC and substation with the trusted PTP backup here shown with this with the arrow. Finally, on the substation, all the PTP backup are provided in terms of performance, but not only on the substation, it could be also at the core. But we know that the PTP at the core is the PTP from a cesium clock or even alternative sources of opportunity if GPS is down. And then finally, GNSS assurance here at the substation, at the core, at any given site. And all that information, all the data here from 1 to 7 is fed into the management system in real time to make actionable decisions while alerting the end user to make sure that the network timing is operational with any given cyber attacks to put the GPS down, or even cyber attack within the network, even PTP or NTP. So here we show the management system provides a self-survival timing chain with trusted PTP assurance. You have another diagram that recaps the above. Here we have 2 sides, but it could be multiple sides down. Everything is green. Why? Because we have the backup from the ePRTC and we have the backup from the PTP. That is the end of my presentation. Thank you. If you have any question, please contact me. Otherwise, the next section is the panel where all the speakers will be joining, and we are welcoming your questions. Thank you.
Hi, everyone. We're transitioning to the panel now. This is actual live panelists. Just real quickly, this slide shows what was just presented, the 4 different topics of resiliency on the left, the 4 different industry verticals on the left, the across the top is the different kinds of resilience and the example that were presented, and the 4 panelists on the diagonal. For the next slide, we'll be able to talk about how to respond to, how to present questions. You should be able to see a question tab on the control panel, typically located on the right of your screen. Feel free to send us questions, and we will address them to the panelists. So let's start out. Let's see. I have a question for Doug Arnold. In the broadcast network with 2 time servers, should they each be cross-connected to both Ethernet sources?
Yeah, good question. In this norm, that's a common way of setting up redundancy in a network, is to have cross-connected redundant grandmasters. But in this case, you don't want to do that. Because what would happen is they would see each other's messages, and one of them would go passive, and the other one would be the active grandmaster. And what they actually want with these dual spine networks is to have PTP information flowing down the spine actively at all times in both networks, so they can quickly, if one of the networks goes down, they can quickly react to the other one.
Thank you, Doug. I have another question. I'm not sure who to address this to. It's about how will the introduction of post-quantum cryptography algorithms impact this in the future, if at all? That is, it could increase the time to verify and authenticate messages. Someone care to comment on that?
The only thing I would say is I think that's all unknown. If full-fledged quantum computers become common, then the whole state of the art for message integrity, authentication, and that sort of thing is going to have to be revisited.
Thanks, Doug. I'm going to address this one to Anand. Notably missing was LoRaN or other proposed wireless backup networks. Care to comment on why these are less relevant or compelling? Though I think I did see a mention of these in your slides. And that's my last addition to the question.
No, I think it's a good question, because my slides mentioned beyond GNSS, but actually predominantly in wireless networks, the backup is still referencing GNSS as its source of time. So it is a good question. What about non-GNSS sources of time? The truth is, in the telecoms and the mobile industry, the methodology of deploying networks has been very much governed by defined and agreed standards, most of which do revolve around GNSS as the ultimate source. So there is a fair amount of I would say, investigation, exploratory work going on with specific companies and specific operators at looking at sources of time, like national timing centers, beacons of transmitted time, other signals than GNSS. So in answer to that question, yes, it's happening, but there's no serious discussion or deployment of these technologies yet, because the industry bodies that govern the deployment models in telecom still focus on guidelines that revolve around GNSS. So in other words, just to summarize my answer, there are other sources, there is investigation going on, but there's no serious work in terms of deployment of sources beyond GNSS.
Thanks, Anand. A question for David Chandler. Please define and elaborate on linearization challenges.
Yeah, thanks. So when I referred to linearization challenges in the presentation, basically it's the concept of what occurred first. If you have multiple replications of the database distributed over a large area, at the end you're going to need to figure out what happened first where, right? So if, let's say, there's a record that was transacted on in New York, and the same record was transacted in Los Angeles, you may need to figure that out. The obvious situation is people like to use the example of, let's say I put a deposit into my bank account, and maybe that was in one database, and then I tried to pay with the money that I just deposited, and that wound up going to a geographically different location. I need to make sure that the deposit in all instances at the end actually shows that it happened prior to the payment to avoid getting any type of fee from the bank. So that's just one of the examples of things where, going back afterwards, after all the transactions occurred, making sure you understand what happened first.
Thanks, David. Here's another question that I think I'll ask Nino, though others might want to comment on it. There's a question about, let's see, it just rolled off my screen, sorry. There it is. Is there a need for local wireless precise synchronization technology? And my understanding is that that would be a synchronization over the air. And is there a need for that? Are there technologies available for that?
So that's a good question. In the power grid, there is actually a wireless technology, not local, but they're using it as an alternative sources of opportunity, and that's basically the NIST as a stratum 0 source, but it's provided to the local side by microwave technology. So I don't know if I'm answering the question specifically, but otherwise, having the source locally available without any kind of wireless technology, I don't know of any other source unless it's independent. It's an independent source. That means that it doesn't work without any radio signal.
Thank you.
Mark, it might be worth adding, so this isn't a source of time, but as a way of transferring it, there are standards for using Wi-Fi to transfer time. And this is aided by the fact that Wi-Fi does have a built-in sort of timing mechanism in the protocol itself.
Oh, thanks, guys. And so here's a question that might go to Doug. What are the best options to ensure integrity of PTP messages? Authenticate, encrypt, it's encrypted tunnels. What is deployed today?
Okay, good question. So the usual thinking for timing message is that encryption is not required. Time isn't a secret. We just want to know that it's the correct time and it's coming from who it says it's coming from. So usually some kind of authentication protection, in terms of a hash code, is what people look at. And in fact, for encryption, then that could interfere with the ability to do hardware timestamping. If the timestamp is not in the clear in the message when it shows up, then it might be hard to do timestamping, right at the layer 1 or 2 when it comes in.
Thanks, Doug. Anand, does 5G cellular network support transfer of timing information wirelessly?
Yeah, so there's a lot of discussions going on about transfer of time over the wireless, whether it's 2, 3, 4, 5G radio interface. Now, bear in mind, coming back to the previous question about wireless timing, Doug mentioned Wi-Fi, but actually all RF wireless signals have timing. Your mobile phone is synchronized by the signal it's receiving from the base station, because otherwise it couldn't communicate. So I think the question, the previous question that was asked was, is there a need, is probably the more pertinent question. Yes, there are technologies. Yes, there are discussions about how you can transfer time. And yes, time is transferred across that wireless signal even today. However, what accuracy or precision of time do you need? And you'll find in this timing industry a lot of discussion around
well, the more accurate or precise your time, the more you can facilitate in terms of services, technologies, and so on. So I think ultimately it's about finding the use case that makes money, that has a business case around it. If there is a use case for your mobile device or any device to get more precise timing over the air, then the technologies will start being further developed and deployed. So the concept exists. The reality on the ground is that timing over the air today is delivered just to make the thing work.
Thank you. So here's an interesting question that I think a number of our panelists might discuss. The nature of GPS attacks is more and more complex. GPS receiver is usually designed with simplicity and cost effectiveness in mind. Receivers, grandmasters are standalone, not talking between each other. To switch to a backup source, the receiver needs to detect its GNS source degradation, and currently the level of the antenna RF signal is a basic tool to detect jamming events. Are there any GNSS receiver technology enhancements on the horizon to make the degradation easier to be detected, and perhaps a little discussion on how this management can detect and transfer to an appropriate backup? Anyone?
Yeah, Mark, there's actually several things being worked on by people who develop GNSS technology. Some of them are very simple, like just having shielding on an antenna so that signals coming from the ground, which might be coming from a jammer or a spoofer, would be blocked. More sophisticated techniques, including having a phased array of antennas that can detect an unusually strong signal that might be a jammer or a spoofer and put a null in that direction, or to detect that it's coming from a direction you don't expect. And also, in conjunction with a very stable oscillator, you can see that time is moving at a rate that seems unnatural for a GNSS system, and so you could say that can't be right, it must be a spoof signal.
Yeah, I also think it would be important to point out, there's a comment that GMs are standalone and don't talk to each other. Actually, there's a lot of them where they do talk to each other these days. So you actually get, quality of service between some of the GMs, and you under each other with multiple time sources to see which GM is actually giving you the best time.
Also, to add to David and Doug, jamming is very easy to detect. Spoofing is the major complexity to detect, and there are two categories of spoofing. There is asynchronous and there is synchronous spoofing, which is extremely sophisticated to detect the latter one, the synchronous spoofing. So we are actually adopting two receivers on a grandmaster, so that one is in fixed mode, the other one is in navigational mode, so you can detect that spoofing or that synchronous spoofing effect by having a redundant receiver on a grandmaster. And so that's kind of one of the way to mitigate jamming and spoofing on a GNSS receiver, on top of using the analytics or the data provided by any kind of GNSS receiver vendor that are providing more and more data for us to process and detect jamming and spoofing.
I'm wondering, David, if you have other comments on ways in which receivers are being hardened for. I'm aware that there's a big push for receivers to be more resilient. Do you have any comments on that?
Sure. Among other things with receivers, people are going away from single band receivers as well, right? So you have multi-band receivers that now receive GNSS, Galileo, GLONASS, Beidou, QZSS. But not only that, even within those, there's different channels. So, you get the L1, the L2, possibly the L5. So we're moving to that, having more bands receivable. Other things that are being done to harden them is there are security messages. In the US, the military just introduced M code, but in Galileo, there's actually a secure service as well available to the public. So there are, specific things being done with hardening.
Thanks, David. I have another question on links and local time transfer devices. How is a link calibrated, and what level of uncertainty can be achieved? I think this could be viewed in many ways, but mainly it's not GNSS, it's other timing methods such as fiber, time over fiber. How do you, obviously you need to calibrate the link in the fiber to get time unless you can do two-way. So would anyone care to comment on how calibrations are done and the need for calibration?
Well, to some degree, I think the need for calibration, when you're doing PTP, you have two-way discussion, right? You're getting the feedback back and forth in terms of the timing of how long it took the signal to give there, what time, the clock perceived it at the location that the end user is using, and then he sends that back. So you almost have a dynamic real-time, discussion going on. And within fiber, you also have very similar things. You can provide synchronous Ethernet as well in there. So it's very much a live situation. If you're going to operate asynchronously, though, and not have a discussion going backwards, maybe, for example, then yeah, that's a real challenge, right? There are systems that measure that that are deployed out there, but they tend to be pretty elaborate. We depend on that two-way communication most of the time.
And how, I mean, the two-way is dependent on the delay in both directions being the same. How accurate is that?
That varies from basically picoseconds to milliseconds, depending on what you're going through. If you're going through switches and routers with queuing noise, it doesn't take many hops to get you into the millisecond regime. But if you look at some of the very precise networks using White Rabbit technology, they get down below a nanosecond.
Okay, one more question is, it's about standardization of PRTCs and coherent network PRTCs. Do you consider its evolution a potential solution on diminishing reliance and consequently on the exposure to GNSS attacks? I might ask this to Anand since it's related to the telecom standards.
Yeah, I mean, I will quickly answer, but we have 3 PRTC experts on the panel other than me, so let them comment as well. Yes, I think there's a lot of discussion going on in the standards bodies, and more than that, there's actual deployments going on in real networks of these considerations and technologies to address exactly some of these concerns. But I guess, sorry, Mark, the question was, are there any updates on that? I probably want to hand over to the other panelists to see if they have any comment on that.
That's one of the major topics of discussion at the ITUT time and sync group is to get the standardization for that finalized.
Okay. I want to move on. I think it's time to end. I'd like to thank the panelists for a great discussion. Appreciate everybody. Thank Addis also for all the work in making this happen. And if we could move to the final slide, I would like to mention and actually some of the details about the workshop on synchronization and timing systems that's coming up in about a month live in person in Denver. All the topics that were discussed here will be, we'll go into a lot more depth on all these topics and other topics. That, as you see on the slide, there are many topics that are presented at WSTS this year. There's the link over on the right, wsts.addis.org, if you want to go there and check in. If you book before April 15th, which is coming up soon, you can get the reduced room rate at the Embassy Suites Hotel, where we're actually going to have our live in person. I'm so excited because it's been so many years since we've been able to do in person. So please consider coming. And I'd like to thank you all for attending. And there will be opportunities to get the slides afterwards and PDFs. And thank you.
Thank you.
Bye.
Thank you.